Welcome to the deep dive. Today we are jumping right into the 2025 Nobel Prize in Physics. This one went to John Clarke, Michel Devoret, and John Martinez for answering a really fundamental question. Basically, does the weirdness of quantum mechanics, can it apply to big things we can actually see?
That's exactly it. It's the core tension, really.
Right, because a ball doesn't just go through a wall in our world.
Never, but for a tiny particle, that tunneling is, just what it does. And so the question, which people like Tony Leggett were asking was, well, what if you have a huge object, billions of particles? Can you make that act like one single quantum thing?
And their answer was a huge yes, and they showed it using, of all things, electrical circuits.
Superconducting circuits, to be specific. They proved two key things: that a big system can tunnel and that its energy comes in discrete packets, or quanta.
Okay, so when you say a macroscopic object, we're not talking about Schrödinger's cat this time.
No, nothing like that. The object here was the superconducting condensate itself.
So all the electrons moving together?
Exactly. You can think of it like a single massive fluid of paired up electrons, Cooper pairs, all moving in unison.
And that collective flow is the macroscopic variable they wanted to control.
That's the thing they subjected to quantum rules.
And the piece of hardware that made this possible was the Josephson junction, right?
The absolute key. It's this incredibly thin insulating barrier that sits between two superconductors.
Just thin enough that those Cooper pairs can quantum tunnel right across it.
Right, but measuring that is, well, it's unbelievably difficult. John Clarke's early work was all about this problem.
He was trying to measure voltages down to the femtovolt range. That's almost nothing.
It's practically noise. And that need for extreme sensitivity led him, almost by accident, to invent this thing they called the slug.
Which was really a SQUID, a superconducting quantum interference device.
It was just a blob of solder on a niobium wire that turned out to be this amazing low-noise magnetic sensor. You couldn't have done these experiments without it.
Okay, so they have this setup. They have the super-sensitive measurement tool. What was the first smoking gun, the first real proof?
The first one was demonstrating energy level quantization.
So proving the energy in their circuit couldn't just be any value. It had to be in specific, discrete steps.
Precisely. They modeled their circuit as a particle trapped in a little valley, what we call a potential well. Then they cooled it way down and zapped it with microwaves.
Okay, and what happened?
The particle, the state of the whole system, would escape from this valley, but the escape rate just shot up only when the microwave frequency perfectly matched the energy gap.
The gap between, say, level 0 and level 1.
Exactly. It's like pushing a swing. You have to push it just the right moment, the right frequency to get it to go higher. That proved the energy levels weren't continuous.
That's incredible. So that proof one. What about the second one, the macroscopic quantum tunneling, or MQT?
Right, MQT. So for that, they looked at the escape rate as they got things even colder, down below 50 millikelvin.
So basically absolute zero.
Almost. And classically, if you take away all the heat, the thermal energy, nothing should be able to get out of that valley. The escape rate should drop to zero.
But I'm guessing it didn't.
It did not. It flattened out. The escape rate became completely independent of temperature.
Which means something other than heat was pushing it out.
Yes. That something was the entire macroscopic system quantum tunneling through the barrier. It was the definitive T=0 signature they were looking for.
And I know they were incredibly careful to rule out noise. John Martinez's team, they used all this intense shielding, right?
Oh, absolutely. They even put copper powder inside their cables to absorb any stray radiation that could have faked the effect.
And they ran a control experiment, too.
They did. They changed the circuit to make it more classical, and just as they predicted, the tunneling stopped. The system went right back to behaving by the old rules.
So the implications of this, it's really what launched the entire field of superconducting quantum circuits.
It really was. This is what allowed us to start creating artificial atoms.
Like the transmon qubits we hear about all the time.
The transmon, the fluxonium. And the amazing thing about these is, unlike a real atom where the energy levels are just fixed by nature.
You can design them. You can actually tune the energy levels just by changing the physical layout of the circuit.
And that tunability is everything. It's the direct line from this Nobel-winning work to modern quantum-limited amplifiers and even the big 53-qubit quantum supremacy experiments.
It essentially turned quantum mechanics from a thought experiment into a true engineering discipline.
That's a great way to put it. And it leaves you, the listener, with this one last provocative thought. We've pushed the scale where quantum mechanics works way, way further out. But there still has to be a boundary somewhere, right? At what point does it finally break down and our familiar classical world take over for good? That's the frontier we're still exploring.